The signature reaction type of carboxylic acid derivatives is called nucleophilic acyl substitution. It's a nucleophilic substitution reaction, meaning one nucleophile substitutes for another, or a nucleophile displaces a leaving group, and it's called acyl substitution because the substitution occurs at an electrophilic acyl carbon. A carbonyl carbon is the electrophilic carbon. Although this is a nucleophilic substitution process, the mechanism is not SN2 or SN1. And before we get into that, let's take a look at this general reaction scheme for nucleophilic acyl substitution to get a sense of what's going on here. So we start with a carboxylic acid derivative. We've got a carbonyl group and the Z group here attached to it. That's the heteroatomic group that's going to function as a leaving group in this reaction. What appears to happen is that the nucleophile, which presumably has a lone pair, uses that lone pair to form a bond to the carbonyl carbon and kicks off Z-. But this does not occur in a single elementary step. It is not an SN2 process. It's also not SN1 with loss of the Z group prior to introduction of the nucleophile. The one exception is a reaction we've seen previously in reactions of aromatic compounds. Back then, we called it an electrophilic aromatic substitution, but from the perspective of the electrophile, it's actually a nucleophilic substitution reaction. Pause the video and think back to our studies of electrophilic aromatic substitution and see if you can recall what this reaction was, where substitution occurred at a carbonyl carbon. It's the Friedel-Crafts acylation reaction, in which we treated an acyl chloride, which is a carboxylic acid derivative, with AlCl3. The Cl- was lost, right, with that AlCl3 as AlCl4-, and that created an acylium ion, and then the aromatic came in. That's kind of an SN1 type nucleophilic acyl substitution, but that's the only place you will see the leaving group come off before the nucleophile adds in this context. We'll have more to say about the mechanism here in a second. The first thing I want to talk about before we get there, though, is when this reaction is thermodynamically feasible or spontaneous in the forward direction, and when it's not. In order for this reaction to be favorable, thermodynamically favorable, go in the forward direction, it is necessary that Z- must be more stable than nu-. So the leaving group must be less nucleophilic than the nucleophilic reactant, the nucleophile. If that's not the case, then Z will have the ability to displace nu as a leaving group, and the reaction will run spontaneously backwards from products to reactants. And so by Z- being more stable than nu-, we mean that Z- needs to be relatively electronegative, needs to potentially have resonance delocalization or some kind of inductive effect, something that's going to stabilize negative charge or a new pair of electrons, a new lone pair inside this leaving group. The leaving group is not always anionic. We can accomplish this reaction under acidic conditions with a neutral leaving group and neutral nucleophile, but the same basic principle has to apply, that either Z- has to be quite a bit more stable than nu-, or in some cases we can take advantage of reversibility and equilibrium and Le Chatelier's principle, using a large excess of the nucleophile to drive this reaction toward products when the reactants and products are similar in stability, when nu- and Z- are similar in stability. All right, so the mechanism is not SN2 or SN1. What is it? Well, here again, it's helpful to think back to prior studies of aromatic chemistry. We've seen dissociative substitution. That's the SN1 reaction where the leaving group pops off and the nucleophile comes in. We've seen concerted substitution. That's SN2, where the nucleophile comes in and the leaving group departs at the same time. We've also seen associative substitution, where the nucleophile comes in, we get a tetrahedral intermediate, an intermediate where the electrophilic carbon, which is trigonal in the starting material, the starting carbonyl compound, becomes tetrahedral and then kicks off the leaving group. Where we saw that previously was in nucleophilic aromatic substitution. Nucleophile added, and then the leaving group was kicked off in a beta elimination step. That same type of mechanism, that same sequence of elementary steps occurs in nucleophilic acyl substitution. So we start with our carboxylic acid derivative and the nucleophile. In the first elementary step, the nucleophile adds into the carbonyl carbon, and we get what's called a tetrahedral intermediate. This is what we called in the nucleophilic aromatic substitution context a Meisenheimer complex, and it was non-aromatic but had a conjugated system and all that jazz. I'll link back to the nucleophilic aromatic substitution video so you can revisit that, and I strongly, strongly encourage you to revisit that so that you can draw an analogy between that reaction type and this reaction type right here. This tetrahedral intermediate has O- adjacent to what is ultimately a good leaving group, or at least a better leaving group than in U, the Z group. And so beta elimination of Z produces a new carboxylic acid derivative with the nucleophile now linked to the carbonyl carbon and Z-. So we have made the product. So this is a two-step associative substitution mechanism with nucleophilic addition occurring first and beta elimination occurring second. This is the canonical or typical, or as I like to call it, default mode mechanism for nucleophilic acyl substitution. And you'll hear it referred to as SNAC, substitution, nucleophilic at an acyl group or acyl carbon, since the electrophilic carbon is a carbonyl carbon.